Hello everyone, and thank you very much for watching. I am Arno from ThinkCell, and I'm the technical director there. And I want to talk to you about a few things that we learned about error handling when writing our software. So errors can happen everywhere. For everyone it's a big pain, and we all want reliable programs. But unfortunately, we don't have any time to write error handling. And the problem is, how do we do it? Before I talk about that, I want to talk about a few of the basics of error handling. So how do we do it? What options do we have to transport errors out of functions? Say you have a file and you're opening a file and the file's not there. How do you know? Well, the classic way to do it probably is a return value. So you cannot do this in a constructor. So you have a function, open say, and it returns either true or false, depending on whether the operation succeeded or not. Another way to do it is with an out parameter. Quite similar. You can now use it in a constructor, but the disadvantage is that you cannot use no discard for checking that you actually didn't forget to check your error value. So both of these approaches clutter the code and are, well, maybe less than ideal. Now, an alternative is a status flag. So there you essentially have a single control path, and whenever you do an operation, your object remembers whether that operation succeeded or not. And if it didn't, then it throws a flag to false. And after you did a whole sequence of operations, at the end you can find out whether your sequence of operations succeeded or not. That's fine in some cases. For example, when writing a file, maybe when reading a file and you need the intermediate outputs, intermediate results, then it's not as good. It's actually the default for C++ I/O streams. Another more modern way to do error handling are monads. The idea there is that you are wrapping the result of the operation and potential error codes into one object, and it's either a result or an error. It's kind of like a variant of the two. And now you have some utilities that when you are processing this result, that you can then just operate on the result and you leave the error alone. So this combination of error and result will actually percolate through your program until at some point you really want to deal with the error and unpack it. So there you have also this advantage of having a single code path, both for the error and for the results. There is actually in C++20, there was this proposal to add this as a library function, as STIT expected. They didn't end up voting it into the standard, but it's certainly, that proposal is still there, so we'll see where it goes. Now, the classic way to deal with errors are exceptions. And before we go into the pros and cons of exceptions, let's talk about some pitfalls here. So you should always catch exceptions by reference, because if you catch them by value, first of all, you may get slicing. So that is, if you have a derived object and you copy it into a base object, then the derived object's part that is not in base will get sliced off. And that may not be what you want. Another disadvantage copying by value is that during that copy operation, when you create that new base object, another exception may be thrown. Something may go wrong. And a double throw will end up terminating your program. So that is certainly also not nice. Another thing also that I should mention is that throw, actually the throw operation, if you just write throw semicolon, it will actually throw the original object. It will not throw the thing that you caught. So if you catch by value, something else is thrown than what you caught, which is maybe a bit surprising. So just catch by reference and everything will be fine. So what are pros and cons of exceptions? Exceptions work a little bit like multi-level go-tos in the code. So when you say here you have a main and you have an increase, and inside the increase there's an if 3 equals I, then it throws something. And that throw makes the control flow leave that function immediately, and then it gets basically it reappears in the increment call in main, and there it also leaves the control flow and goes to the catch clause. Now, I could be a little bit mean and say, well, really, it's a bit like a go-to, right? So it could look something like this. So you have when 3 equals I, then we have a side channel that goes out of that function. Here it's an out parameter, just imaginary out parameter. And you just assign that exception to this out parameter. You somehow transport this value out, and then you do a goto out of that function. You simply return with some dummy return value. And but that's not enough. When you are then receiving that exception in main, again, it has the effect of a goto. You're leaving the current control flow and jump to the exception handler. And when you have a lot of exceptions in your code and many things throw that you're writing in your control flow, that produces a lot of extra code paths. Effectively, you have, well, it's spaghetti code, but something close to it. You have many code paths, which is actually a good reason for people not to allow exceptions in the code altogether. There are some code bases that just simply don't allow exceptions. Now, of course, you could say, stop whining. What are you complaining about? Of course, you must write exception-safe code. Well, what do we mean by exception-safe code? Well, what we're really talking about is not just pertinent to exceptions. It's really about any error handling that a function, or any errors that a function could produce. And it's part of the specification of the function of how it deals with an error that occurs. Now, of course, the best you can have is a function that just never fails. It will always work, and then you have no problem. Unfortunately, it's pretty hard to achieve. So the next best thing we could have is a strong exception guarantee. What we mean by that is if that function fails, then it will restore the state of the program back to what it was before the exception was thrown, or before the error occurred, before the call of that operation was made. So you essentially get everything is rolled back to what it was before. It's, in the database, you'd call this a transaction. That's certainly possible and desirable when you're implementing library functions, and the std library functions usually have that property. But it's very hard to do in application code, because applications usually change a lot of states. So you have a lot of state changes in sequence, and you would have to remember all these state changes so you can roll them back when something goes wrong. And even rolling back may not always be possible, because when you're doing something that is influencing something outside of your program, I mean, rolling that back may actually again throw an error, and what do you do then? So that's very hard to do. Now, the least requirement you could have is the basic exception guarantee. And that means that if the function fails, it will leave the program at least in a valid state. So in some state that the program can carry on with. Well, I would think this is nice, but does it really help? So imagine there is a customer calling Microsoft and say, hey, I just had Windows deleting my whole document. And I would like to complain. I would like to have this fixed. It's like Microsoft says, no, it's okay. That's fine. It's fine that it does that, because we only have the basic exception guarantee, and an empty document is a valid state. And then this customer says, oh yeah, that's great. Thank you very much. Thank you. Well, probably this conversation will never happen. So the customer just wants to get work done. So any state will just not do. So what do we do? Here's the challenge. Error handling is a lot of effort. In development, we have to be really paranoid. Anything can fail. We have to constantly think about, okay, what do we do if this fails? We will write a lot of extra code for it. We will handle all these errors and think for every single one of them, what do we do if that happens? And then, after we wrote all this code and we got this big headache, the testers come and they have to test all these code paths that we generated. And as we all know, if they don't test them, they won't work. That's all very frustrating. So, on top of that, what's the benefit for the customer? Almost nothing, right? So the customer wants to get work done. He doesn't care, she doesn't care about all your error reporting code that you wrote. So, what do we do? How do we solve this? Of course, we had this problem as well at ThinkCell, and we had to think about what to do. And here's what we did. First of all, we check everything. Every API call that we make is checked whether it succeeded. Now, that means you basically have a wrapper per error reporting method. In Windows, get lost error or hresults from common functions. In Unix, you have Arno. So we have different wrappers that check these things and make sure that the call succeeded. We have lots of asserts that assert aggressively and they stay in release mode. So they're not thrown out when we ship the program to the customer. They stay in. All the functions that are not expected to throw exceptions are actually marked no except. This may seem to be overly aggressive, but if your program doesn't expect exceptions to come out of a function, then probably it will go wrong anyway. And so if you write no except, then the C++ runtime will call std terminate. But, well, it's not likely to be much worse than an exception that is ultimately not actually caught. And we can install a handler inside with set terminate. We can install a handler that actually reports these cases and allows for debugging, but I'll come to that later. Now, after we checked everything, we made sure that we check every single error return. We then assume that everything works. So we don't write any error handling code. We just check. So what's the goal here? Why do we do this? Well, first of all, we want to ensure that everything works, of course. But the second goal is that we want to keep the set of code paths really small. We want to keep the program on this narrow path of correctness. We don't want it to stray out, and we handle all these cases where it strays out from this narrow path. We want to keep it in a really tight path where we are really certain about the states that the program can take on. And most of the bugs in programming come about with state. If you have unexpected state that the programmer did not foresee, that creates bugs. And we want to avoid that. We want to keep the program on this narrow state, in this narrow state bound. Now, what do we do if things fail? Of course, all these checks that we built in, they may fail. What do we do? Well, the priority one is we have to collect as much information as possible. We need this information because we now need to understand this bug. We need to understand whether this failed API call or this failed assertion, why did it fail? And we have to fix it, and possibly we now do have to write error code for it. But for that, we need information. So the client, when it happens on the client out with the customer side, we actually set the core poem to contain some information. The server actually halts the thread that is currently executing. And that's the best freezing of state you can have, where you can introspect the system really well. If the threads are just stopped, and you can now attach with a debugger to your server and see what's gone wrong. The priority two is carry on somehow. I mean, as you see, the server just halted a thread. Maybe the user can restart its operation, do a different request. But for the client, you can carry on. Now, if the check that we had there was critical, this is an API call that we did not expect to fail, then we say the program behavior from now on is undefined. So don't make any further reports, don't collect any further information, because the program now is an undefined behavior. We don't want to know anything anymore about what the program is doing, because this just may be a consequence of that failed API call earlier. Now, one important thing here is, even though we are now in undefined behavior, I call this undefined behavior land, don't terminate. Assertions may be wrong. And if you terminate when an assertion is violated, then your programmers, the developers, will be afraid of writing assertions. They shouldn't be afraid. They should write aggressive assertions. And in order to encourage aggressive assertions, the only thing you can do is carry on if an assertion fails. If you need extra safety for that, if you say, okay, if an assertion failed, oh, that's dangerous because now my program may be corrupt, my data may be corrupt. Solve this in a different way. Save repeatedly. Have some extra safety net in a nuclear power plant that that drops the control rods when you have to stop the machine. But add this at a different level. Don't add this into your program where you say if an assertion fails, that's, oh my God, I'm now all scared, I'm going to terminate the program, because no one will write assertions anymore. Now, one example we had actually in our code is that when the server, I said that the thread is actually stopped, is actually halted when we run into an assertion. And we actually stop processing requests of a certain type if there are too many outstanding threads of that type. So if basically all these threads got stuck somehow of this kind of request type, we just stop processing this request type so it doesn't pull down the whole server. And at some point we have only threads that are all halted. But this is a different level. I mean, of course, the problem there, it may not be that an assertion fired. Maybe just someone wrote an infinite loop, and then the same argument should apply, that we actually just have it at a different level, because it doesn't really matter. Infinite loop versus a infinite sleep that basically fired because of the assertion that failed. There's not a whole lot of difference. What do we have to do next? Well, we have to reproduce the error in the lab, at home. You have to understand the error, because you don't want to just write blind error handling code of errors that you don't understand. The thing is that you probably, from experience, very frequently it happens that you think it's one thing, that one reason that this assertion failed or this API call failed, but the actual reason is a completely different one. You think that, oh yeah, my graphics card call failed, maybe I have to repeat it or whatever. Well, it turns out that the graphics card driver is bad, and the person should update the graphics card driver, and it always occurs with versions less than 3.4. Well, what shall you do then? Well, you should probably tell this person that his graphics card driver is less than 3.4 and he should go get an update. And that's something very specific for one particular API call that failed, which is you cannot simply understand by looking at the failed piece of code. You have to reproduce the error and then understand under which circumstances it occurs. And very frequently, these circumstances are important, and they are also the key to prevent the error altogether. You may not have to write error handling code. All that you need to do is you have to check when you install the program, is my graphics driver up to date? And then the problem will never occur, and then you don't have to handle it. Now, if you do that, it turns out that you only need maybe for 2% of the API calls, you actually need error handling. All the other ones succeed all the time. And this makes you focus on these 2% that actually fail. And they are actually producing all the errors. So if you just spread your effort throughout all the error handlers, if you would have done that, you would have really wasted your time, but still not addressed the problems that are really causing the reliability issues in your program. Now we want to be a little bit more specific about what we do with our errors, because we separated these errors in several categories. And I think it makes sense here to go through these categories one by one and to understand what the kind of different levels are of problems that you may encounter and how you want to react to them. The most severe case of errors are errors where it is very unlikely that they will stay unnoticed, where you're really sure that this is a serious problem in the program. We usually have things like if you are about to access a null pointer, will crash the program. But also if there is an API call that you expect to succeed, and that API call fails, then clearly there's something will go wrong in the program. Very probably there was a reason you put this API call there in the first place. So what do we do? If you're on the client, we actually put up an error dialog. We say, hey, there's a problem. So if the program subsequently crashes, don't be too surprised. And we also give the user an opportunity to contact support, to actually get help with the error. Now, one level down from that, and it's still undefined behavior. So the first one is undefined behavior for sure. This is behavior that you did not program for. The program is undefined in this case, that the result won't be good anymore. An assertion failure is really one level down because assertions usually don't have side effects. So it is very possible and actually quite frequent that we developers, write wrong assertions. And in that case, we already said, don't terminate the program. And we also say, don't disturb the user. Don't tell the user the assertion failed. The idea again is there, don't put up any obstacle to any developers writing assertions. You want to make it easy for developers to write assertions. Even though then if the assertion fails, the program is undefined, the program result is undefined, that's still no reason to disturb the user. Maybe the assertion is wrong. And so what we do there is just to disable future reports. We just say, okay, by definition, the program behavior is undefined, but we still have hope. We just carry on. And maybe it was just a wrong assertion. Now, when we go one level down further in severity, then we're now crossing into the realm of defined behavior, where you have, I say this is the border to undefined behavior land here. And now the programmer actually programmed for this case. And there are rare situations where you essentially have, you know that this problem may occur, but you have never been able to test it. So, for example, you are wrapping some memory allocation function, and you're being called from somewhere, and the memory allocation, you wrap the memory allocation function, you do the memory allocation, and of course this memory allocation may fail. I mean, all you need to do is to allocate enough memory, and that memory allocation will fail. But maybe in the context that you wrap that memory allocation function in, say you are wrapping it inside some host application, into some other application that you didn't write, you've never seen this allocation to fail. So it's not so clear how that host application would react if this memory allocation fails. This is a case for what we have here as level 4. We still want to report this situation if it occurs, because we've never been able to test it. So maybe if we do a report now, if we send information about this error, maybe then at home in the lab, we can actually reproduce it. And then either make it critical and say, oh, the host application cannot deal with it at all. If there's a memory allocation that fails, it will immediately crash. So no point carrying on. Or we say, okay, that's fine. That can happen once in a while, and we can then downgrade it further. But there is this level of things that are basically untested. We have it here as level 4. Level 3, if there may be problems where the user experience is just not good. It's defined behavior. You know that it can occur, but it's really rare. And you didn't really flush out the code. You maybe put up an error message and say, yeah, sorry, it didn't work. But, or maybe a little bit of user data that gets deleted. And you know it happens once in a million. And you know, it's okay. Maybe you even have something where that you in this case, you probably would have something that reproduces this error in the lab. You know how to get there, but you say it's very unlikely that it's relevant for the user. What we do in this case is we at least log it in any case. We log the error so that when people actually call us and say, well, we've actually seen this error, we can take a look into the log and then confirm, yes, it's this error that we thought doesn't occur. And then maybe we have to change our mind about handling it or not. Now, if you go even further down, now we are actually in a situation where the user experience is good, everything is handled, everything is fine, but the situation may still be an indication for something else. It may be an indication for a broken environment, for example. An example would be that you cannot access a directory that you usually are able to access. And maybe that's something that the user wanted, but maybe he doesn't know about it. You don't really know. You cannot really judge it. And you put up a proper error message, everything is fine, but maybe even then it's something where you would say, maybe this is something you would like to know, that, for example, certain groups of users have this directory be inaccessible. Now, the least amount of errors that we can have, and there what we actually do, I should complete that, is that if you're running in in a debug mode. So we have a way that the application actually runs in a debug environment where the support engineer contacted the user, attached to the user machine, and ran the application. And in that case, if we run into the situation that is a somewhat broken program environment, we put up a dialog box and we put up a warning and say, this is a behavior that may be an indication that this environment is unusual. And then there is the level 1 error, the lowest error. And there really, it's the question only of, does this occur at every single time the program runs? If it occurs every single time, there's really no point logging it. It's a regular operation. For example, if every time you iterate through a collection, and at every time at the end of the collection you run into the situation that the collection is now at the end, well, that's not surprising. It will happen eventually. But and that you wouldn't take care of at all. That's not even a bug, or not even something worth logging. But there may be a situation where a situation that you want to log still. You don't want to put up a message box, but you still want to log it for engineering, the support engineers to look at, so he understands something about the control flow of the program, things that occurred while the program was executing. All right, so these are the list of or the categories of error that we distinguish. We do a fair bit of an error analysis, and I said already that you shouldn't really address problems until you understand them. And what we do is, when something goes wrong, then we send reports with a core dump to our central server. That happens automatically, and if the user doesn't like that, then he can send them manually by email. And we have an error database where these reports are filed into. The core dumps for that purpose are open in a debugger, and then the error is automatically categorized. It's automatically looked at which line in which file it occurred. And it's put into the error database. So for each error, you have several occurrences at the user sites that you can browse. And these details for each occurrence of any specific error are then accessible to the developers, so they can actually take a look at the information and hopefully find a fix for the bug. Once the bug is fixed, developers can actually mark errors as fixed. So they can say, okay, this is the version that fixed my bug. And then when someone is encountering the bug, it would actually look into the database and find the update, and potentially not show an error dialog to the user, but instead ask the user to update to a new version. This can also be done by email. So when someone decides not to have automatic updates, but sends the update by email, this email is immediately bounced and says, hey, you can just update to this new version, and then your problem will be fixed. And this is something that people find close to magic, when they send an email and immediately get a response with a solution. That's quite cool. Now, I want to talk at the end about a feature that would influence error reporting quite a bit. It's C++20 contracts. It's actually a new language feature. It's a little bit assert on steroids. You can declare certain function preconditions and postconditions as part of the language in your function declaration. And of course, when you have such a feature, there are many questions that come up. For example, when do you check these conditions? Do you check them only on debug? Do you maybe check them as well on release? There was also the idea that maybe some of them you can never check, but you could potentially use to optimize the program. And now, if you do check, what do you do if the check goes wrong? Do you terminate the program? That's something I would recommend against. Do you carry on? Or then if you either terminate or carry on, do you report before you actually do that? So do you send a report somewhere? Which information do you send? And where do you send the information to? Many questions. The thing is, C++20 contracts were actually removed from the C++20 standard at the last minute. So this whole discussion about all these questions will continue for C++23, for the next version of C++. All right, thank you very much for listening. And yes, we are recruiting. Here you have the email address. Just send us a quick note and we'd be very happy. And thank you very much for listening. Thanks.